All right, yeah. Thank you. So we're going to talk today about dynamic healthcare dataset generation, curation, and quality with PySpark. I know that's a mouthful. But really the goal of this talk is to present a framework that we've built at Modernizing Medicine for performing ETL, modifying data, and on top of that, really building in and filling in some gaps with the Spark framework, because Spark is really great for big data processing. It's really the go-to engine for that. But there are certain things around it more related to metadata, checking the quality of the data, that we've used Python and some of the object-oriented stuff that you get with Python to fill in the gaps. So hopefully this will give just little bits of wisdom for you to bring back to your organization to help improve your processes. So I'm going to breeze through a couple of these introduction slides just so you get an idea of who we are as Modernizing Medicine and what we do as a data team. We are a software as a service platform that offers several products for doctors to use in their offices. One of our main specialties is in dermatology. We have around 45% of the market in the US for private practice dermatologists. So any sort of software that a doctor will need to run their practice, from documenting clinical data to billing, financials, scheduling appointments, and anything that they might need, we have a bunch of software to support that. And the way we accomplish that is really through this three-pronged approach. And it starts with a mobile-first product. So the doctor is using an iPad at the point of care, working with a patient. There's phone apps. We even have a watch app. And, of course, a web app when you need it. And the software itself is built upon structured data. So there's very minimal free-form dictation or free text input into the EHR system, so that way you actually have structured data points where you can have actionable insights come out of that data rather than locking up a lot of this clinical information inside of free text. And that's all built on top of the cloud to enable us to really deploy new versions faster to keep everybody up to date, as well as having a uniform data input system, which is one of the differentiators for our product, that everybody that uses our software records data and has the same workflow, and we can benefit from that and have knowledge that we learn from the masses of doctors and patients that we're collecting data on to be able to help improve care. So this is the part where I convince you that we have big data. We have tens of thousands of users on our product. Those are staff members that are actually day in and day out using our products to see patients and to perform care. And with that, we're seeing hundreds and thousands, or at least the doctors using our product are seeing hundreds and thousands of patients every single day. And over the last probably around 7-8 years since the product has existed, that's accumulated to over 100 million patient encounters throughout the United States. So this is in thousands of different doctors' offices, millions and millions of patient encounters and patients, and we're collecting structured clinical data from them. So really, this talk is focused more about what our data engineering team does and the tools that we use. And so basically, we have a set of data products that we create to benefit our business as well as our customers. So that everything starts in a centralized data warehouse, and then from there, we pretty much think of every other data set that we create as just a downstream data extract. And so we're pulling data from that centralized data warehouse that collects data from all of our customers, and then you're either serving the business internally, we're giving the data back to the customers, doing analytics in the application or whatever we may need to do. And this talk really isn't about infrastructure, but just again, to give you a high-level overview of what we're doing and how we're doing it, Spark is the main processing engine for everything that we do at Modernizing Medicine. And the way the data originates is from MySQL databases. So these are the application databases where the iPad apps are sending data back into here, and then everything's recorded in these application databases. We have it split up into multiple shards just for load balancing. So what we do is we pull data in from those MySQL servers, we perform some ETL, create our data warehouse, and then we save that off to S3. So to keep the storage and the compute decoupled, we'll use Spark clusters, spin up Spark cluster to do our processing, and then we save the data onto S3 to persist it. And then again, from there, we have downstream places where we put our data, whether it's into a BI tool, into some sort of extract that we land on S3 or a file server or whatever. And these databases are humongous. If you're thinking about just structured database information, to have over 600 gigs of that in each of these shards, and we have multiples of these, and that's not even including any unstructured data like images or anything like that. So there's a really, really lot of data that we have at play here. And so really what we're here to talk about is this dataset generation framework that we're building with Spark, but particularly with Python, because we can benefit from a lot of things in the Python ecosystem. And yeah, that's me in the corner there, so I couldn't help myself, I had to throw myself in here. So looking from a clinical perspective, this is really the problem that we're dealing with. When you think about patient data and collecting clinical information, a lot of the data is going to be the same no matter what context you're looking at. So in our case, I'm showing a couple different examples of a couple diseases on the right here for data sets for psoriasis and melanoma, which are skin conditions, and then macular degeneration, which is an ocular condition in the eyes. So all three of these data sets are going to have a lot of uniform data like demographics, sex, date of birth, age, things like that. And they're all going to have the same data. It's all recorded the same way. So the demographics table is probably going to look exactly the same for these three data sets. But when you go down into some specifics, you're going to see here that psoriasis and melanoma data sets are really going to care about skin conditions because doctors are recording information that may be related to whatever condition that the patient may have. But for macular degeneration, you don't really care what kind of skin conditions the patient has. But even across specialties, like looking at the purple one, the injection there, you're going to inject medications for psoriasis, but also you may inject medications to a patient for macular degeneration. So even across specialties, there's some shared data points there. So this is what we're trying to solve is we don't want to have to rewrite ETL every time we're creating a data set. We want to be able to have uniform tables and data elements, but we also want to be able to pick and choose in certain scenarios which data elements we want. And so we didn't just start from the beginning and say, hey, okay, we have this problem of creating data sets, so we're just going to build this object-oriented framework on Python with Spark and spin up clusters dynamically and use Airflow for scheduling and all this stuff. It really didn't happen like that. How it happened was I got there, I was hired as a data scientist, the first person on the data team, really, and they were like, our DevOps team was basically like, here's a 5-node Cloudera cluster, go do data things with it. And so looking at it at the time, right, well, maybe 4 or 5 years ago, the de facto structured big data processing engine really was Hive. But it was just too slow. For the size of data that we had and the size of the cluster that we had, it was just too slow and it just wasn't happening. So we were like, okay, what else do we have here? Well, instead of Hive, why don't we try Impala? So Impala really is an analytic engine. It's a SQL engine on top of Cloudera clusters, and it works really well for analytics, ad hoc queries, and things like that. But we were kind of using it for something that it wasn't necessarily made for ETL. And the issue with that was that our cluster was sized 5 years ago for the size of our data 5 years ago. But adding 100,000 patient encounters every single day, you quickly outgrow that. And it's not an elastic cluster, so it started to fall over, and we were starting to have some problems. In addition to that, when you're writing straight SQL, if it's simple, it's very easy to read, really simple. But as soon as your SQL query gets over 5 or 10 lines, you have multiple subqueries, you have window functions, you have all these different things, it starts to get really complex. And then if you're taking that and copying and pasting it for every data set that you want to make, it just becomes a whole mess. So we tried to fix it a little bit with some string manipulation for injecting variables, but it kind of felt like a Band-Aid solution and really wasn't the full solution. So what do? We went to Spark, and specifically, we used PySpark. I'm not going to lie, the main reason why we used PySpark at first was because nobody knew Scala. Nobody wanted to learn Scala. And there's just a lot of pain points with the whole JVM and dependency management with Maven and all this stuff that kind of didn't want to have to deal with. And so we're playing around with Python, and we're like, okay, Python's easy to use. Spark has APIs for Python. And when we started doing this, it was right when 1.6 came out, so the data frames API was out, and it was very easy to start to build on top of that. And of course, Spark 2 kind of really enhance a lot of stuff. So, not just the Spark part, but specifically Python, you get a lot of good stuff with the Python ecosystem because of the big scientific community using Python. So you get things like pandas and NumPy. It's very easy to jump down into there if there's any reason we need to do that. And just little things like JSON files are treated as dictionaries in Python, so it's very easy to interact with them. And there's a whole bunch of packages for you to do whatever you need to. One of them that we use is for reading and writing Excel files. So what I want to do here is really give some examples and show some code a little bit, some simplified code really of some of the abstractions that we built into this package. And there's really two main themes when you're thinking about this framework that we built. One of them is abstractions, and the other is reuse. So this first one here is an example of some file abstractions that we built. And what this is, Spark has a bunch of different connectors for reading and writing different sources, right? So default, you can read Parquet files, you can read from a database, from JDBC, you can read and write text files. But you still have to know which specific methods you're calling. You have to add the arguments properly. So what we did here is create a parent class called data directory, saying by default it's going to be Parquet files that it deals with. So you initialize the class, you give it a path for where your Parquet files are, and then we use those getAttribute and getItem methods to make it easy and clean to load tables and specify tables here. And then from there, you can just create child classes of that parent class and say, okay, well, instead of Parquet files that we're going to use, we want to use a Hive database, or we want to write text files. And so when you initialize these classes at runtime, you can set your arguments there, like separators or quote characters or whatnot. And then every time you use that class to read and write files, you don't have to think about it anymore. The idea is really to pinpoint the ETL to where you don't have to think about reading and writing files. You don't have to think about all these other things. You really can just write your logic for your transformations. And I'll show an example of how this is used in a second. So that's abstractions. When you talk about reuse and the problem that we were having of copying and pasting SQL queries everywhere, the idea is to just write ETL for some data element one time, and then you can reuse it across the board wherever you want to. And then on top of that, you can add additional functionality by creating a child class of a certain table if you need to. So the way we abstract this is have a parent class for table definition. So there's a class for every table that you want to create. And this parent class here has a couple methods. Particularly, there's a make method that we have, which every child class is required to implement. And that's where the logic for your actual ETL goes. So around that, you can see in the constructor here that you pass the source and destination objects, which were those classes that I showed you before. And so now within the actual ETL, all you have to do is say self.source and then read a table from there. And then in your make method from your child classes, that's where you actually put your real logic, and that's where you're writing your Spark code using the data frames API to actually perform these transformations. So this is a really small end-to-end example, and I'm going to highlight certain pieces of the code so you can follow along. So the way we structure all of our data sets is that we create one Python module per data set, and that's what's on the bottom half here, the init.py file. So what this does is it enumerates all the tables that you want to include, and they can live in different places if you want to structure your code in different ways. You basically have different modules for different levels of tables that you want to create. So for instance, we have our set of generic tables, and then we might have a set of dermatology tables and a set of ophthalmology tables, or whatever we may need. And then from there, you can set a couple specific parameters around your data set, and then kind of go from there. So, and then the top half here is an example of just one table that I'm showing the ETL for. So the first bit, like I said before, each table is a class. And in that class contains the actual logic for the ETL that you're creating. So here we define the class called derm patient, and then down in the module we say, okay, this is the first table that we want. It's the fully qualified path for wherever that lives, and then say I want the derm patient table. And then here's an example of that file abstractions that I was showing you. So rather than inside of the ETL having to do spark.read.parquet, go put in an S3 path or whatever path you're trying to get the data from, here I just say I know because I am a child of this table definition class that I have a source object. And this source object interacts with whatever type of files that I have. So this may be a MySQL database, this may be text files. It doesn't matter to you. When you're writing the ETL for the code, all you want to be able to do is just load a table. So in this case, we're saying I want to load the diagnosis table from wherever it happens to be. And from here, so there's a little piece on the bottom and a little piece on the top. So when you want to be able to reuse ETL, there's kind of two aspects that you need to think about. One is your table structure, and then the other is the data that's actually inside it. So basically your rows, how do your rows get in there? And so there's two ways that we help with reuse in this perspective. So in this particular case, I want the structure of the derm patient table to be exactly the same for no matter what data set uses this. But if I'm creating a data set in the context of a specific disease, like I'm showing here for acne, I don't want to include patients with every type of disease. I really only care about acne patients. So in this case, we set this class variable called inclusion diagnoses at the bottom there on the table definition parent class. And so every child class of table definition now is going to have this inclusion diagnoses class variable set to that set right there with the two values. So within the ETL, I don't actually have to touch the code in the ETL to change my inclusion criteria. I just say filter the diagnosis table to be whatever that class variable happens to be. So then at runtime, obviously this module gets loaded, and then all the parameters get injected properly, and then your table gets created. You only have to write the ETL once. And on the other side, that's to keep the structure of the tables consistent and then change how the rows get in there. But if you want to actually add additional columns to a table, it's actually really easy to do, and you don't have to rewrite code all the time. So the scenario that I'm showing you here is that you have a generic patient table, and let's say that patient table has the ID of the patient record, sex, date of birth, and then maybe some sort of geography elements. And that's going to be the same for no matter what kind of data set you're creating, no matter what specialty or disease you're in. But in this scenario, I'm creating an acne data set, so I want some additional information about specifically from dermatology. So rather than having to rewrite the ETL from my patient table to go find the age and sex columns and everything, all of that's written already, so I just call the make method of my parent class and say, run all the Spark code, generate the ETL for that patient table. Now I have whatever columns I need. And then at the bottom here, I join it together, and then I just say, grab all the original columns and then slap on a couple additional ones specifically for dermatology. So you can see how these have become building blocks now. We can kind of just keep building more complex tables that are inheriting from parent classes. So putting that all together, again, this is our example of creating small data set, and you're injecting different parameters, and the idea really is to write ETL once and then reuse as much as possible. So some other nice things that you get from Python is you get PyCharm, the whole IDE, and this is just an example of some of our unit tests passing. And so, of course, they're all passing. They're always passing. They never fail. And really, the unit tests aren't really on the ETL of the logic of the ETL. It's more around all the helper functions. So if you're making abstractions for reading and writing files, you need to make sure those things work. You're not reading and writing the wrong files, that everything is working properly. And so that's actually the suite of tests that I'm showing here, is just on those reader classes. And you just get other things like autocomplete and whatnot. And the one thing that we also didn't get when we were using Hive and Impala was that basically we tested everything and built everything on production. So the only way for us to write code and run code was to go log into Hue and write some SQL and then see if it works. What you get with using Spark and specifically with Python is now you can actually have local dev environments where we have some QA data that we put locally on our machines. You can write your ETL and make sure that that stuff passes, and then deploy it to some sort of staging environment to make sure that it's going to work with the size of the data that we're working with. And then once all that stuff works, you can work through any bugs and then finally deploy it to production so everything can run smoothly. So that was really about generating data sets. But it's one thing to just go make a bunch of data. It's another thing to actually support anybody who's using the data, and then also making sure that it is what you say it is. So that's what we're talking about here with curation and quality is first metadata about the actual data to make sure that people who are using it can use it properly, and then you want to make sure that you're actually giving out what you say you are. So the way we kind of accomplish this is with creating a JSON file that represents the schema of every single data set. And within that JSON file, we have things like the table names, the column names. We say whether columns are primary keys and put some descriptions for each thing, as well as certain quality rules that we want that particular data element to adhere to. And from there, it's actually this nice lightweight kind of data object where we can pass around, and let's say we want to generate a data dictionary based on the metadata that's in that JSON file. And then on the other side, we can even use the metadata that's in that JSON file to power whatever quality checks we want to run on the data. I do want to give a quick shout out to this webinar that I watched probably like 2 years ago from Smartsheet and Databricks. I honestly have no idea what they were talking about. I don't remember. But what I do remember is that they gave me this little idea to use JSON files to capture the metadata. So I think that's really what the benefit of talks like these and conferences and webinars and stuff is, hopefully just give little bits and ideas that you can kind of bring back and take to your organization. So thanks to them for that. I have one slide here just on the data dictionaries. There's really not a whole lot that's going on there. Basically, it's taking this JSON file on the left We are specifying some tables and the names and some descriptions for each. And on the right side here, we run it through a Python script. It uses the XLSX writer Python package, and then we spit out a nice, pretty Excel file. And that package is fantastic if you've never used it before. It's integrated with pandas. You can basically do anything that you would ever need to do in an Excel file, but from code. So you never have to touch it manually. So what we do is we click a button on the JSON file, generates this Excel file, and then nobody has to touch it later. It's really, really helpful too, because now we can actually put version control around the JSON files. Whereas with an Excel document, it's really hard to track changes. Anybody can make changes to it and say, like, hey, you were supposed to give me this table, and it's not there in the data. But we can go back to Git, and go back to source control, and say, no, actually, this is what the original data dictionary is supposed to look like. And then you can change colors and do whatever you need to and make things all nice. On the quality side, this is an example here of, again, a simplified data set with the JSON file describing the metadata. So on the quality side, the way this works is that you have an input JSON file that specifies your metadata. It's the same thing that produced that Excel file. And then it runs through Spark. It performs checks on all the tables and all the columns. And then it spits out another output JSON file with the results of all those checks. So I'm going to highlight a couple examples here. So here's an example of just one single column. And this column here is on the patient table. It's the patient ID column. And we're saying it's a primary key. It has 11 characters, and here's the description of it. And then another column here, we have sex. And this one particularly is an enumerated value column. And we're saying the only values allowed in this column are male, female, and unknown. So at the bottom here, we say, run this rule called accepted values on the patient.sex column. So when we pass this into our quality engine, it's going to parse the JSON file and then execute this accepted values rule on the patient sex column and then spit out the results of that. So this is the full example of the output file on the output side. And it has a lot of the same metadata that the input file had. But what happens here is every single data element now has a rules object that enumerates all the quality rules that were executed on that particular data element. And so in this particular case, we ran a rule called row count that says this table has this many rows, and then we can go look at this document later to see how many rows the table has. And looking at the sex column, we can see, okay, this rule, this accepted values rule actually failed. So there were some extraneous data in this column. It's not allowed to be in there. What this does when the engine sees a failure, it's going to halt the job. It's not going to deliver it to any downstream consumers. It's going to alert our data engineering team. We have to go in, investigate what's wrong, either fix the data, deploy a new version, or kind of let it pass and then tweak the quality file. And to give you an idea of what the code looks like for these quality files, again, it's the same idea of abstracting away as much as possible. It uses the same library for reading and writing files that I described a few slides ago. But in this particular case, we're saying there's a few different levels of quality rules. So there's certain things that you might want to enforce on an entire data set and say, this particular data set has these many tables, or it should have this name, or whatever. There are table rules like row count, or making sure the table is not empty, making sure the table name is correct. And then specifically inside of the column rules, there's a whole bunch of rules there for like checking that primary keys are unique, checking that foreign key references are good, field lengths, accepted values, and whatnot. So this is an example of the accepted values rule. The actual Spark code for running this is pretty simple. It's on line 9 here. It's just you filter it, grab the column that you're working on, find rows where that column has values that aren't in your list. And then if there are some, you spit out a failure. If not, everything is good, and you can just go ahead and pass. So it's really simple. And again, it's to isolate the logic. We have classes for every single rule, and inside of there is really where you're writing your Spark code using the data frame API to write your language for the quality checks. And then you can reuse this rule as many times as you need it. We have this running on every single enumerated value in all of our data sets, all of our tables, all of our columns. So that's really the overview of this entire framework that we have, and I just want to give you a quick idea of how this all fits in together. This isn't really a talk on Airflow or automation or running things in production, but I want to at least just show a quick screenshot, just give everybody an idea. So basically in here, we list all of our jobs. These aren't actually our real jobs. I wasn't allowed to show the actual production data. So you can see that some of these jobs run on schedules down here. Some of them are manual. And then here we can see when jobs are failing. So let's go through a particular scenario where we have a job that's running every night. And then we see this little red circle. And we're like, oh no, something's going on. Something's wrong. So the way we check that is actually through this UI that we're prototyping, and what this is actually taking the output, that output JSON file that ran through the quality job, and it's putting it into a UI. So every time we run a data set, we spit out that quality file into a directory on S3, and then we have this plugin into Airflow that reads all the files from S3 and then displays it up on the screen here. So we can say, okay, data set number 1 yesterday failed. So I can go in here, click through, find data set number 1, click on yesterday's run, and then see all of the rules and which ones failed. And I can click through and then isolate which particular column and element that was. And then now I have some ideas of what I need to do to go and investigate that. This just makes it a little easier rather than having to sift through and search a JSON file. You can actually see everything here in a nice UI. And the Airflow project is really fantastic for this too, because we didn't have to actually touch any of the guts of Airflow. It has a plugin interface where we just added an extra Python file, extra HTML file to put this up, and then we got this new tab here. And we don't have to deal with the credentials and everything. Airflow takes care of all that stuff. So just to show kind of our team, this is the contributors to our project on the data engineering team. Don't let my title fool you. I do come from a computer science background as well. And so I kind of play on both sides of the fence of data engineering and data science. So that's why I'm kind of presenting this framework here. So with that, again, my name is Aaron Richter. I'm a data scientist at Modernizing Medicine. I'm also a PhD student at Florida Atlantic University. I'm doing some research on early detection of melanoma, basically. And if you're interested in coming to Florida, there's not as many alligators as people make it seem. We are hiring. We're hiring hundreds of new jobs in the next few years. So there's probably something out here for you. So thank you.
Thank you again, Aaron. We have a couple minutes for questions, and I just want to let you guys know that there is a healthcare and life sciences meetup tomorrow after the Spark Summit in the afternoon.
My name is Jaya. I too work for a healthcare company. My question is specifically this healthcare data, right? We get from multiple providers, right? And this is the whole thing is about data cleansing and transformations, right? Mm-hmm. So when you say, for example, basic things like, when you get the data from providers, say the narrative column, right? It could be a field number 5 from customer 1, like provider 1, and field number 10 from provider 2. Right? How do you handle those type of data attribute mappings, mapping issues?
Yeah, and so I think the benefit for us is that we are the EMR as well as the data processor. So we have a structured database where all that data is going to be uniformly collected for all of our providers that are using the software. So in that particular case, a prescription is going to be written the same way. It's going to be going into the same database table, and it's going to be marked accordingly. So that way we can be able to differentiate and know which one is which.
Hi, nice talk. My name is Axel. I also work in a healthcare company. So how long did it take, or how long did your team take to actually put this into production from the start?
Yeah, so we started developing this probably beginning of last year and went into production. I mean, really, it didn't take a whole lot because we kind of continuously built on this. We probably went into production after like 3 months of developing it. Of course, we've built on more and more things onto that. That's really on just the ETL side. We were still running things manually. For the Airflow side, to actually get it orchestrated and running on a schedule, that probably took another 3 months to get everything going because the project itself is less mature, so there's less documentation on it. We kind of had to watch like meetups and watch different videos and figure it out. But once we got it deployed and working, it's been running now for a few months and no problems.
This question may be too health specific, but I imagine Modern Medicine is a business associate per HIPAA, so you actually have no issues joining data of various types because you already are dealing with protected health information? And
yeah.
If not, then how are you dealing with HIPAA issues around PHI?
Yeah, so I mean, we are a covered entity, so because doctors are actually recording their data into our software, so anything where it's servicing our customers, which are the doctors and the patients, we're fine to use PHI. We have to use the PHI. For any scenarios, we do maintain a de-identified data warehouse that we get validated through the, there's a HIPAA clause, I forgot what it's called, but there's a way you can kind of de-identify data to be in line with HIPAA, and we do that. In any case where we don't need PHI to do any analysis, we'll just use the de-identified data warehouse. It's safer that way, you're not dealing with identifying information. Yeah, absolutely. So that's the challenge. It's like we have to make sure that our ETL is strong, that we design our data sets really well, because then you have to go back through that whole iteration over and over again.
All right, guys, we're going to break for lunch, but you can always grab Aaron. Thank you again, Aaron.
Thank you.